Section: Introduction. In this section, we discuss how fine-tuning can significantly improve the abilities of large language models. For instance, we can enhance reasoning skills by fine-tuning with chain-of-thought data or boost performance on specific tasks with domain-specific data. However, we must be cautious, as these improvements can sometimes compromise the safety of the models. Even harmless training data can lead to serious safety issues during standard fine-tuning processes. Therefore, it is essential for us to ensure that while models gain new skills, they also retain their safety features. We face several challenges in maintaining model security during fine-tuning. These include overlooking how benign data affects safety, having limited methods to adapt, and dealing with high computational costs. To tackle these issues, we need to understand how to prevent the loss of a model's safety knowledge. Research shows that the first few tokens of a model's response are crucial indicators of its safety. Based on this insight, we propose a method to preserve the model's safety capabilities by previewing the initial tokens of answers. Our approach involves adjusting the training data to include these answer prefixes, which helps reduce the loss related to them and minimizes disruptions to the model's initial outputs. We introduce LookAhead Tuning, which consists of two straightforward and efficient methods focused on data. This approach successfully balances improving performance on specific tasks while keeping the safety mechanisms intact. By previewing the initial tokens of answers, LookAhead Tuning offers a solid solution to reduce safety risks during fine-tuning. To clarify our discussion, we define some notation. We denote the parameters of the pre-trained model as theta 0, while theta represents the parameters we optimize during fine-tuning, and theta star indicates the optimized parameters after fine-tuning. The dataset is represented as a collection of input-output pairs, where each input corresponds to a specific output. We also define the number of tokens in each output and the loss function used in our optimization process. Additionally, we assess the safety of the model with a function called safe, theta, and we use Kullback-Leibler divergence to measure differences in output distributions. In standard fine-tuning, we adjust the model's parameters to minimize the loss function. Previous studies have identified key factors that affect model safety during this process, particularly focusing on the initial tokens generated. We have shown that the safety difference between the fine-tuned model and the original model is negatively correlated with the Kullback-Leibler divergence of their output distributions over the first few tokens. Our approach includes two methods for ensuring safety compliance by modifying the training data without changing the model's architecture. The first method, real answer, directly incorporates the initial tokens of the correct answer into the training data, guiding the model to generate these tokens while preserving its safety. The second method, virtual answer, uses a neutral prefix to avoid revealing the actual answer, thus maintaining safety while allowing the model to learn effectively. Section Summary. In this section, we discuss the importance of fine-tuning large language models while maintaining their safety, highlighting challenges such as the impact of benign data and high computational demands. We propose LookAhead Tuning, a method that previews answer prefixes during training to enhance performance and preserve safety, utilizing two approaches: real answer, which incorporates actual answer tokens, and virtual answer, which uses neutral prefixes to avoid revealing specific content. Section: Inference. In this section, we describe our inference process, where we adhere to standard fine-tuning methods without altering the inference data, ensuring practical application. To ensure reproducibility, we use greedy decoding for generating responses. For our setup, we fine-tune the Llama 2-7B chat model using the GSM-8K and Samsung datasets to evaluate utility and safety. In our LookAhead tuning methods, we preview 6 tokens for the real answer approach and use the phrase, "Let's solve this problem," as a buffer prefix for the virtual answer approach. We compare our methods against several baselines, including the seed model, vanilla fine-tuning, SDFT, and constrained SFT. We measure utility through accuracy on the GSM-8K dataset and Rouge 1 scores on the Samsung dataset. Safety is evaluated using the raw safe rate and jailbreak safe rate, with assessments made using the HEX-FI dataset. More details about our experimental setup can be found in the appendix. Our main results, as shown in the table, indicate that our LookAhead tuning methods perform well in safety evaluations and downstream tasks compared to the baselines. The real LookAhead tuning achieves the second best performance in terms of safety and utility by only changing the instruction. The virtual LookAhead tuning reaches state-of-the-art performance by modifying both the instruction and the answer, ranking first across all metrics. These findings highlight the effectiveness of using answer prefixes to enhance model safety. Additionally, our real and virtual methods require only a small increase in computational time compared to vanilla fine-tuning, demonstrating their efficiency. The real variant performs well under strict computational limits by modifying instructions with clear prefix guidance, making it suitable for low-resource situations where revealing the first few tokens of answers is acceptable. In contrast, the virtual variant aims to protect the initial tokens while only slightly increasing resource use compared to the real variant. By modifying both instructions and answers with prefixed content, this approach prevents the exposure of actual answer prefixes, achieving optimal performance while maintaining safety. We also analyze fine-tuning safety in relation to the change in KL divergence of the first few tokens. To conduct a thorough safety analysis, we evaluated all models from our main experiments on the harmful HEX-FI dataset, calculating the KL divergence of the initial tokens in responses to harmful prompts compared to the original model. Our method shows a significant reduction in KL divergence for the first few tokens compared to the baselines, while the values for later tokens remain similar. This pattern suggests that our model produces smaller changes in the initial tokens, enhancing safety. This result supports the theoretical framework we presented earlier, indicating that lower KL divergence in early tokens corresponds to increased model safety. We also explore how previewing real answer tokens affects model safety and downstream task performance through experiments on the GSM-8K dataset. Our findings show that increasing the number of previewed tokens enhances safety, but this comes with a trade-off, as the model's performance on downstream tasks often declines. Thus, we must balance the number of previewed tokens to maximize safety while minimizing negative impacts on task performance. Lastly, we assess the robustness of the virtual answer method by testing two variations of the prefix: a coherent phrase, "Let's deal with this situation," and a nonsensical string, "Dajalsa SDFGHKJZMNB." The coherent phrase performs comparably to the original template, while the nonsensical string results in a slight performance drop due to its lack of coherence. Nevertheless, our model maintains strong safety measures and effective performance on downstream tasks, regardless of prefix variations.